Dear students, welcome to the session. This session is dedicated for discussing the question and answers from the chapter Design of Keys, Splines and Couplings. So the first question we have is define the key. A key is a machine element which is used to connect the transmission shaft to a rotating machine elements like pulleys, gears, sprocket and flywheels. Next is the types of keys. The keys are classified on the basis, that is, one of the basis is the part of key is in the shaft as well as in the hub, and there is the majority of the part of key is only in the hub. So when the part is between the shaft and hub, it is called as sunk key. So under the sunk key we have rectangular and square key. Next we have is gib head key. Next is feather key. Next is woodruff key, round key and tangent key. So this is the list of keys under the category of sunk keys, and in saddle keys there is hollow saddle key. Next is flat saddle key. Moving to next question, write the function of key. So here the primary function of key is to transmit the torque from the shaft to the hub of meeting element and vice versa. The secondary function of the key is to prevent the relative rotational motion between the shaft and the joint machine elements like gear and pulley. In most of the cases, key also prevents the axial motion between the two elements, except in the case of feather key and splined connection. So basically the purpose of the key is to make shaft and gear or pulley as an integral part or a single body. Next is define the spline. Splines are the keys which are made integral part with the shaft. They are used when the relative axial motion between the shaft and hub is permitted. The gear shifting mechanism in the automobile is going to make use of the spline. Gearboxes require such type of construction. Splines are cut on the shaft by milling and the hub by broaching. Next question, name and recommend the materials used for the keys and splines. So first material is mild steel, carbon steel for higher strength, alloy steel for heavy duty and high torque application, cast iron when the shafts are of cast iron and loads are moderate, and stainless steel for the corrosive environment. Next is design the keys based on the different modes of failure and also based on the empirical relations. So now this is the shaft. This shaded portion is called as shaft and the outside portion is called as hub. So you can see some portion of the key is inside the hub and another portion is inside the shaft. So here due to the motion by the shaft, there might be the sliding of surfaces is likely to happen. Due to the sliding of surfaces, the key might split into two halves. This is the top half and this would be the bottom half. The sliding is going to be tangential. It is going to get sheared off into two pieces. So this is called as shearing failure. And this would be the length and this would be the width. So now here we can write applied torque is equal to T is equal to, that is, force into diameter by 2. D by 2 is the diameter of the shaft. Okay, and force here is expressed as shearing resistance or shear stress into shear area. This is shear area. That is L by L into W into D by 2. This is for shearing. Let's say this is equation 1. Next is, in the key, as it is interfacing shaft as well as hub for some portion, so half of the area is likely to suffer the crushing. So here we can write the torque as force into diameter by 2. Later, instead of writing shear stress, it will be replaced with crushing stress into the dimension would be T by 2 into length. So T by 2 into length into D by 2. This is torque. So now if we take the ratio of equation 1 and 2, that is T and T will get cancelled. Sigma, that is next will be tau by sigma CR. T by 2 will be there and L and L will get cancelled. So along with T, there will be W. Along with sigma CR, it will be T by 2. So the empirical relation for W, that is width, and thickness generally that is followed is D by 4. So now if you substitute over here, then this is equal to, that is tau by sigma CR, W is D by 4, and in the denominator it would be D by 8. This is equal to 1. So we get this as tau by sigma CR equal to 1 by 2. So ratio of shearing stress to crushing stress is 1 by 2. And we can also express the length, or the empirical relation for length and diameter of the shaft could also be written. So let's say this is equation 1 and this was equation 2. And torque of shaft can be written as pi by 16 d cube into tau. Let's call this as equation 3. And now when we equate 1 with 3, then tau and tau will get cancelled, and this is equal to, L would be becoming equal to pi d by 2, which is 1.57 times of d. So this is another empirical relation that could be derived out of here. That is L is equal to 1.57 times of d it would be. Next question is, write the proportions of a spline. The proportions of a standard spline are shown. So D, that is minor diameter or the root diameter of the shaft, is 0.7 times of major diameter of shaft. Width of the spline is 0.25 times of major diameter, and thickness is 0.125 times of major diameter. So these are the proportions or empirical relations that needs to be followed whenever the spline is being designed. Next, define the coupling. Coupling can be defined as a mechanical device that permanently joins two rotating shafts to each other. The most common application of coupling is joining of shafts of two separately built or purchased units so that the new machine can be formed. Functions of coupling is to connect the two ends of the shaft together, transmit power from one shaft to another, reduce vibrations, provide mechanical flexibility, permit misalignment of the shafts. Next is classify the types of coupling. So there are two types of coupling. One is rigid coupling and the another one is flexible coupling. Under rigid coupling, we have sleeve or muff coupling. Next is split coupling, clamp or split muff coupling, and next is flange coupling. Under flexible coupling, we have is Oldham coupling, next is universal coupling, next is Bush bushed pin type coupling. Next question, design the muff coupling for the shaft of given torque using empirical relations. So first is design of shaft that has to be done. Design of shaft that is given by the equation T by J is equal to tau by R, and this we have already seen many number of times. So upon simplification, that is J is pi by 32 d power 4 and R is small d by 2. So tau here will be equal to, that is 32, or tau here will be equal to T by pi by 32 d power 4 into d by 2, which is 16 t by pi d cube. Next is design of hub. So the size of hub that is given by capital D is equal to 2 times of small d plus 13 mm, and L is equal to 3 times of, or 3.5 times of shaft diameter. Small d is the shaft diameter. This is called as shaft, this will be small d, and this would be capital D. So even hub will be subjected to twisting moment. So for hub, T by J will be pi by 32 capital D power 4 minus small d power 4 is equal to tau into capital D by 2 it would be. So this upon simplification, that is shear stress of hub is equal to, that is 2 ones, and this would be 216. So 16 into torque into capital D divided by pi into capital D power 4 minus small d power 4. Next is design of key. So which we have done already, that is 2 equations will be there for key, that is torque is equal to shear into shearing area, shear stress into shearing area. So shearing area will be happening when the key is split into half. So that is width into length into d by 2. This is for shearing. And for crushing it will be sigma cr into t by 2 into L. L is the length of key, small l we need to follow, into small d by 2. This is for crushing. So design of muff coupling is going to include design of shaft, design of hub, and design of key. So all these steps needs to be followed, and the empirical relations are also written for the hub as well as length of the hub. And even for key also you can write it as small w, that is width of the key, is equal to thickness equal to d by 4. So these are the empirical relations that needs to be followed whenever you're designing the muff coupling. Next question, very important one. Design the cast iron flange coupling for the given torque. First is we start with design of shafts. Design of shafts already that has been done. So torque or design of shaft. So shear stress can be expressed as tau for shaft is equal to 16 t by pi d cube. Next, this portion is called as hub. So for design of hub is modeled as a hollow shaft. So for that, shear stress of hub is equal to 16 into t into diameter of hub, that is capital D, divided by pi into capital D power 4 minus small d power 4, that is design of hub. Next is design of key. The procedure for key is going to be same, that is torque is equal to shear stress into shearing area, that is width into length of the key into d by 2. This is for shear. Next is for the crushing, it would be sigma cr into T by 2 into L into D by 2. This is for crushing. Now here you are finding the sudden increase in cross section at this location. So for the flange, due to sudden increase in cross section, the flange is going to suffer shearing stress. So design of flange, that is here, due to sudden increase in cross section, the resistance might increase or may set up within the material that may shear off the flange. So applied torque is equal to, that is, shearing stress of flange into the diameter where the resistance is being developed is capital D by 2 into shearing area. Shearing area will be lateral surface area, that is lateral surface area would be pi into, that is capital D, into thickness of the flange. It is TF is the thickness of the flange. So this is the design of flange for the shearing failure. Next is, after the design of flange, the bolts will be subjected to shearing as well as crushing. Bolts will be subjected to shearing and crushing, because there might be some relative motion between these two portions of flange, and that may tend to shear off the bolt into two different pieces. The bolt may be sheared off into two different pieces from the middle. So let me just give you the overview. So this is one portion of the bolt, and the other portion, this is how the bolt will be sheared off. So shearing of bolts, that is equal to torque, and bolts are present at a diameter or at a location of capital D1, which is 3D. So capital D1 by 2 into shearing stress induced in the bolts and shearing area of the bolts, that is pi by 4 D square. So this is the shear area into number of bolts into N we need to multiply. Next is crushing of bolts. So crushing here, it will be crushing stress into crushing area. So when the bolt is being crushed, it is going to look like a rectangle. So the lateral surface is going to be crushed. So crushing stress into crushing area, that is diameter into thickness of the flange, into, next, the bolts are present at a location of capital D1 by 2. Capital D1 by 2 into number of bolts. Into number of bolts. So in the cast iron flange coupling, there will be, first we start with design of shaft, then it goes with design of hub. Design of key is repeated in most of the couplings. So this is a common part. This is also a common part. Even design of hub, this has been common with muff coupling or sleeve coupling. Design of flange is a newly added part, and design for the bolts, even this is also newly added part. So if you start with muff coupling, then you are finding the step 1, 2 and 3 repeated. Step 4 is the newly added, step 5 is newly added, and step 6 is newly added. So you can expect a long answer type question from the flange coupling in the final exams as well.